All right, good morning and welcome back to Precalc, everybody. So last time we were sitting here and we were looking at this S-curve, and we're going to go ahead and explore this a little bit. We gave us the formula. Okay, so when we're going to be interpret the meaning of the context. What was P0, right? And P0, that means when we first started, right? So T equals 0 represents 1900. This is the population of the United States in 1900. So we're looking at this, and we could get a better estimate because we can just type this into the formula, right? Do something clever like this, where we're going to have, there we go, like a pen. Okay, so we have 740 over 1 plus 8.345 e to the negative some stuff, negative 0.0175 t, right? And we set when t is equal to 0, then we were going to have 740 over 1 plus 8.345, which is a fancy way of saying 1 over 9.345. And then that's how we're going to get our values here. That's our first thing. All right, so we're going to have 740 divided by 9.345. Oops. Okay, and there we go. So 79.179 million people. Okay. So it was about 79 million. 1900. Use the function to approximate population in January 2020. Okay, so that would be good because that's recent. So this is 740, and then we have 1 plus 8.345 e to the negative 0.0175. And then how many years is how many years is 2020 been since 1900? Okay, so that's 120 years, right? And we have to go through and do that. All right, so you'll forgive me because the calculators that I started on worked backwards. So my calculators kind of did this part, then this part, then this part, then this part, and then the top. Okay, so we just kind of work backwards here. So this was negative 0.0175 times 120. Okay, and we're going to take e to that number. Okay, and that's our answer. That's the previous answer. All right, we're going to multiply that times 8.345. Okay, and then add that to 1. Right, and now we're going to take 740 divided by that answer. Right, and we ended up with 65.99366 million. Okay, so by this estimate, we're a little over. Okay, I think there's 330 million people right now, but we're a little over, so that's going to be 366 million. All right. You always go to like uscensus.gov and figure out the actual real number that we think we have in this country compared to what we have here. So that's, something you guys can do. Use the function to approximate the U.S. population on January 1st, 2070, round to the nearest million. Okay. So again, how many years, right? We have 2070 since 1900. That's 170 years. Okay. Seems unreal. So we have 740, and then here again we have 1 plus 8.345 e to the negative 0.0175 times 170. Okay, so you guys are getting ready to retire. This is going to be the population of the United States here. I guess too big. You guys are about 20 years old now, so it's 50 years in the future. Okay, so we have 740. Oh, actually, never mind. I'm going to do it the other way. I'm just going to say negative 0.0175 times 170. That takes care of my exponent. Okay. Second function, e to that previous number, times 8.345 plus 1. And then we're going to take 740 divided by that number. Okay, so that's, boy, that's quick, isn't it? So between 2020 and 2050, you guys are going to be looking at quite the growth here. Okay. Probably not quite that much because, again, this doesn't account for, well, 500,000 people is not really going to put a dent in overall population growth, but assuming you don't get a worse pandemic in the future. All right. This is a little bit off, so already we know it's like this is not going to quite be that many people, but because you need people to make more people. Biology works. All right. So for the model, during which year would the population reach 600 million? Okay. So this one's going to be a little bit more interesting for us because what we have to do is, right, we have P of T is equal to 740 over 1 plus 8.345 e to the negative 0.0175 t. And this part of the question is saying, well, when is it going to happen that we're going to reach 600 million? So we're going to put 600 on this side, okay, and then we're going to have all of this on the other side. So at its core, this is a rational expression, right? I mean, not really, because rational expression is like polynomial over polynomial, but the structure is the same, right? We got a thing we have to divide. So what I'm going to do is I'm just going to push this to the other side. I'm going to cross multiply effectively, right? So what we're going to have is 1 plus 8.345 e to the negative 0.0175 t, because I multiplied this over here, and that's going to equal 740 over 600, right? So dividing by 600 and multiplying by this piece here. So 1, not a I. All right. So let's go ahead and at this point, right now it doesn't. I mean, it's still scary because there's an E in it. I get it, but it shouldn't be quite that bad now. We've solved problems kind of like this before, maybe with numbers that were a little bit easier. Okay. So let's subtract 1 from both sides. So we're going to have 8.345 e to the negative 0.0175 t, and that is equal to, we subtracted 1, so we have 740 over 600 minus 1. And what I might do is decide that 1 is really 600 over 600. I mean, effectively, we are going to be, using a calculator in a moment. So if you guys wanted to say, what are you doing now? Just using a calculator. Like, that'd be fine, okay? Because the next step, right, is to divide by 8.345, and I'm not going to do that. Right, so we have e to the negative 0.0175 t. That is equal to 14 over 60, all divided by 8.345, right? Let's go ahead and simplify that. So we have 14 over 60 divided by 8.345. All right, so we've got this mess over here, right? So we have e to the negative 0.0175t, and that is equal to 0.02796 and some change. We've got a variable in the exponent position. How do we get the variable down from the exponent position? Well, we take a log of both sides. And then this exponent bit that comes down in front, so we have negative 0.0175t is equal to the natural log of this thing. And then at the end, right, we're just going to divide. We're going to say t is equal to the natural log of 0.02796 and some change, divided by negative 0.0175. Okay. This is why I left it in the calculator, because we could take the natural log of the answer, that's this whole thing, right, and divide it by negative 0.0175. You don't really need to put the zeros in there. You know this is going to be a positive number. So t, right, is equal to 204.4-ish years. Okay, so this is going to be the year, right? We've got 1900, and we're going to add 204 years to that. So we're going to end up in 2104. Okay, so let's see if your grandkids retire, or if you retire in 2070. Good Lord, that just seems so far away. But it isn't. It isn't. It goes quick. You'll be there before you know it. Enjoy the time while you have it. That'll be 40 years after that. So your grandkids will get to experience an America with 600 million people in it, provided nothing bad happens. So here we go, 2104, or nothing good, like we actually end up going to Mars. All right, what value will t? It was t goes to infinity. Okay, so that we talked about this at the beginning, right? Was as let's look at this formula again, right? We had 740 over 1 plus 8 point, what was it, 345 e to the negative 0.0175 t. So this t gets bigger and bigger and bigger. E to the negative t, here's the graph, right? This is e to the negative t. Even if I multiply a small number by it, right, like 0.0175, it's just going to move this. It's just going to move this thing this way a bit. Okay, meaning that there's going to be more space here for a longer period of time. But as time goes off to infinity, right, that gets smaller and smaller and smaller. So no matter what you do, this term here, this whole term is going to go to 0. Meaning, and it's not just the e to the 0, it's this whole thing, right? This whole piece ends up going to 0 as time goes off to infinity. As time marches on, this whole thing goes to 0. So this thing goes to 0. So what we're going to have at time infinity is going to be 740. This is the carrying capacity of the environment that you've put your critters in. So if you've got a lake with goldfish in it, this would be 740 goldfish would be the maximum amount of goldfish in that lake. With us, with humans, this is technically what somebody thinks. This is the maximum carrying capacity of our country. Okay. This term goes to 0. And then the limiting value for P, that's the 740. Oops, 740. If you have a nice species that doesn't really engage in a lot of violence like goldfish, this just pretty much, they just stop having babies, right? And they just kind of live in their maximum capacity. You get a species like rats that are a little bit more violent toward each other when they get to this level, then it's a little bit more unpredictable. I hope none of us ever have to see that. So that's a thing. Okay, and this is almost the same thing. So we could move on to just a different context, but we use this for disease modeling very often. Okay, so you're going to see like if you look at COVID charts for this year, you're going to see a graph very much something like this. Okay, and again, it's got like an S type of a curve to it, where whatever this is considered your maximum. Okay. So the number of computers in millions infected by a computer virus can be approximated by, okay, T is in months after the virus was first detected. Okay, so determine the number of computer viruses initially infected. Okay, so by the time you found out, what do we have here? We have N of T, this is equal to 2.7, 1 plus 16e to the negative 0.7t. All right, so when t is equal to 0, that would be this, right? N of 0, we ended up with 2.7, 1 plus 16 e to the 0. Right? Negative 0.7 times 0 is going to be 0, and e to the 0 is 1. So this is going to be 2.7 divided by 1 plus 16, 17, and we're going to end up with 2.7 divided by 17. Okay, so about 0.1588. What units did they want this in? So that was a good question. Okay, and approximately round to the nearest 10,000. Okay, well, this is millions, right? This is in millions. So what was this point? What? 0.1588. So this is 100,000. This is 10,000. So 0.17 million. Okay, or 170,000. Oh, how do they want me to say this? When you get this, the answer is wrong. Please check carefully. Let's double check. Oh, it should be 1.6, not 1. Okay, because, yeah, 1.6. How did I do that? Oops. Let me check. All right, there we go. How many computers were after 6 months? Well, what's my time measured in? Time is in months. Okay, very good. We don't have to do anything weird. Because it could be in days, right? And then we'd have to figure that out. But thankfully, we are in months. So what we're going to do is we're just going to plug in. We're going to say, well, this is n of 6, right? Because we're looking at 6 months. So this is 2.6, 2.7 rather. 1 plus 16 e to the negative 0.7 times 6. All right. So let's go ahead and do that. So 0.7 times, negative 0.7 times 6, 4.2. And then e to that number, times 16 plus 1. Okay. And now we're going to take 2.7 divided by that. So 2.7 divided by that number. We got 2.17 and some change. So what do they want for my nearest 10,000 again? So we're going to be down here, second digit. Okay, so we want 2.17. Add second digit, that's going to be 2.18. Okay, so 2.18 million computers. Oh. because yesterday we did this and it yelled at me for not putting the commas in. Go figure. Okay, determine the amount of time required after initial detection for the virus to infect 1 million computers, round to the nearest 10th of a month. It's a weird measurement, but okay. So again, here, right, this is the number of computers that are infected. So we'll start with our n is equal to 2.7, 1 plus 16, e to the negative 0.7 t. And they're saying that they would like 1 million over here. Right? And n is in millions of things, I think. It's the beginning. N is in millions. So they want 1 million. Right, so we have 1 is equal to 2.7 over 1 plus 16 e to the negative 0.7 t. And again, we're just going to cross multiply this. Okay. In this case, we don't really need to divide too much, right? This is just going to be 1 plus 16 e to the negative 0.7 t is equal to 2.7. And we're just going to carry on through this. So subtract 1 from both sides. All right. Divide both sides by 16. Okay, so we're going to say this is e to the negative 0.7 t is equal to 1.6 divided by 16, or 1.7 rather, 1.7 divided by 16. And that's 0.10625. Yep. And then we've got a variable in the exponent position. How do we get that down? We're going to take the natural log of both sides. By the way, the goal really is to make you so bored of these and to say, oh, these are so easy. I would be so happy if you look at this and you say, oh, these are too easy. Could you come up with something harder? Because that means when you see these on exam, you're going to nail them. You're just going to hit all of these right out of the park, and I could not be happier. And when you guys get done, your grades will come back. You won't be happier either. So it's all good for everybody. All right. So natural log 0.10625. 10626. Come on. All right. Divided by 0.7. I know it's going to be a positive number because this is negative. This is negative. I just didn't put them in. Okay. So that was 3.20. They usually say go to the nearest. Oh, they went to the nearest 10th of a month. So they don't need that. You just need this. So it'll be in 3.2 months. 3.2 months after initial detection. Okay. What is the limiting value of number of computers infected according to this model? Okay. Well, it's asking us the same thing what happened last time. It's saying, well, if t goes on to infinity, right? If t goes off to infinity as time tends toward infinity, okay. What was our original function here? It was 27 or 2.7, 1 plus, what was this? 16 e to the negative 0.7 t. Yeah. Okay, so again, right, this is e to the negative. If I just look at this piece right here, right, 16 e to the negative 0.7 t, that's the same thing as, right, because the negative thing means it's a fraction, so it's 16 over e to the 0.7 t. Okay. Now as time gets bigger and bigger and bigger, right, this t to the positive 0.7, this gets, that does that. So as time marches forward, this thing gets really, 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 really big. And think about it, right? If I take 16 and I say, well, 16 divided by 1,000, what's 16 divided by 1,000,000? What's 16 divided by 1,000,000,000? All right. by the way, if you guys don't know how to put that in your calculators. Nobody's actually asking you to do that, but in case you ever had to, 16 divided by, and it's 1, oh, let me do parentheses. Okay, it's 1. It's not EE, like, it's not this E. It's not this little green E. It's this second. It's this green EE. That's how TI says times 10 to the. Okay. So that's what we get. It's just going to get to be a really, really, really small number. So this whole piece here, this goes to 0. So all we have in the end here is 2.7 divided by 1. So they're saying the maximum number of computers that is going to be affected by this virus is 2.7 over 1. All right. And that's where we are. All right. This is a really important skill, and you'll get better at it with time. This is not something that you're expected to master immediately, although it's a good thing, because humans, we are really good at finding patterns, right? We could look at a cloud and we can say, well, that looks like a dragon, or that looks like a butterfly. We do this in my statistics class because they get charts, and they get stuff that looks like this. You say, how would you model that? Like, well, I would try to draw a line through that, is what I would do. So looking at this model, right, it looks like it might be leveling off here, but I don't really have enough to say that that's going to happen. So at this point, I would look at that and I would say that looks like it's going to be linear. Okay. That's the most, and humans like linear. Most humans, this is just a nature of our species, right? You look at like some kind of a health measure, and then how much vitamin D, let's go this way, vitamin D, and some kind of a health measure. Usually that's what's going to happen, right? You take somebody with no vitamin D and you start giving them vitamin D, and their health gets better. So people will look at that and say, well, if some was good, then more must be better. Like, well, not with those vitamins, because they're what they call fat soluble, and they don't come out. So you could take too much of any of these. D is kind of a hard one. A is you can take too much A. Okay, but that's what's going to happen to your health after a certain point if you take too much. I should have picked A, vitamin A. But yeah, we think more is better. If someone's good, more must be better. Like that is not true. Okay, so in some cases it won't matter so much, right? You can give somebody vitamin C, and what's going to happen with their health is something like this. I know it's possible to give somebody too much vitamin C, but it's a lot. Okay, it's really a lot. So that's not really something you want to do. Okay. But it's just asking you to look at the shapes and say, what do you think it is? Okay. So this one, right? And we're being real careful about what kind of patterns to give to you, because, you know, we do this in my stats class, like I said. It's called scatter plot. We give them a thing. And you'll see this, right? You'll have, I swear to you, you will attend presentations where you'll get this as data, and somebody will say, obviously, it's linear. Like, really? Are you sure you can make a line out of this? I mean, you can, but are you sure that's really the right choice? So if you're looking at a cloud of dots and you're like, I see a butterfly. No, you don't. You don't see a relationship. In this case, that looks exponential. Okay. Now, is it parabolic? It might be, but more things are exponential than they are parabolic. So we're going to go with exponential. Okay, and that's, again, you're going to get, if you take more science classes, you're going to have more experience with different models, and you're going to see a little bit more of what's going on. This one has the curve in the other direction. Is it a square root? It might be. It wasn't the choices I was given, so of these choices, I would go with something like that. But, and again, logarithmic is more common than square root, But and as you take more science classes, you'll get that. But pretty much you're trying to match the general shape to the shapes that you already know. Okay, so that's the whole goal of this stuff, is to how about this? And tomorrow I'll show you COVID. Okay, I'll show you COVID graph, and you'll see this one a lot. Okay, but this has that S curve to it, right? That is the S curve, so that's going to be logistic. Okay, that's what we think. It's not linear, right? Because it levels off and it starts leveled off. It's not logarithmic because it would just be, this part would be logarithmic. And it's not exponential because it would just be that front part. Right? But this is why we made you learn all of those shapes, was so that when you get data, you can look at this and say, I think it's approximately this shape. And that lets you come up with a formula to model. Okay. All right. So let's see. But by the way, this is, you do a lot of this in statistics. So if you like playing connect the dots, that's a good field for you to go in. Okay, let's do one more of these. I don't know what I'm going to do for you guys tomorrow. I think we'll probably go back and maybe hit some of this stuff again tomorrow and do some of these problems again. But okay, so here we go. We have Q of t is equal to Q sub 0 e to the negative 0.000121 t. Okay, it says use this model. Great. It says here is a sample from a mummified bull. It was taken from a certain place. We have 72% of the carbon that still remains. How old is it? So we have 72% remaining. It didn't tell us how much it was. Doesn't matter. So if you want to decide that you have 100 here and you have 72% of 100 over there, that's fine. You're going to get the same answer if you decided to have 1 and 0.72. Or if you had 3, whatever 0.72 or whatever 72% of 3 is. Okay, it won't matter. So like I said before, if you're taking an exam, you're doing something, and you're like, you ask the teacher, I'm like, what was the mass? And they say it doesn't matter, then I invite you to put whatever number you feel is convenient in there, because if it doesn't matter, then whatever your pick shouldn't make a difference. And in this case, whatever your pick is, you're going to end up with 0.72 is equal to e to the negative 0.000121 t. Doesn't matter what your pick is. You're always going to end up in this spot. Okay, so here we have a variable in the exponent. What should we do about that? Well, we should take a natural log of both sides, of course. All right, so this guy here, this is going to come down in front. And t is equal to natural log of 0.72 divided by negative 0.000121. I know this is going to be a negative, so if I'm not going to do the negatives, it's okay. Because anything under 1, right? The natural log graph looks like this. This point, this is 1, 0. And the natural log graph looks something like this. So anytime you have a fraction like 4/5, 2/3, right, 1/7, it's always going to be over here somewhere. These are all going to be negative numbers. So what do we have? We have natural log 0.72 divided by 0.000121. And we get the t is 27, we'll call it 2715. Again, I really have problems with this because I would say that because we have 2 significant digits, but the computer is our friend and we will obey. Okay. All right. So so there we are with that was 3.6. That was our logarithmic and exponential modeling. What I'll do tomorrow is I'll bring in some of my homegrown problems so you could see how I rate them. And I'll show you some COVID stuff tomorrow because you'll see these graphs. And for the countries that handled it better, you'll see these graphs. Okay. So we'll do some COVID stuff tomorrow. We'll do some homegrown problems, and then I might give you guys a survey or something to say what out of chapter 3 would you like me to go over and hit. I know everybody always says all, okay. But what would you like me to spend the most time on for chapter 3? We'll certainly do a lot of this stuff because I know the word problems are going to be a big hit. But yeah, that's pretty much all I have for today for us. So I'll let you go a little bit early, and tomorrow we'll do some more problems like this. And next week is an exam week, so we will set that up for us and do a review next week. Okay. Again, test is not going to be due until next Sunday at midnight, so I'm not gonna, that stays the way it is. Okay. So thank you all for coming today. Actually, let me go ahead and stop recording.